How far can human curiosity really reach before the universe stops answering back at the outer limits of what can be observed? NASA's instruments have begun to notice details we never expected to see with the power of the James Webb Space Telescope. Star nurseries emerge from darkness, and ancient galaxies come into focus far beyond what Hubble once revealed. Beyond them lie the quiet outskirts of our own solar system, where Voyager spacecraft continue their silent journey into interstellar space. And farther still, entire clusters of galaxies appear to drift towards something unseen, beyond the edge of the observable universe itself. If thoughtful journeys like this speak to you, please like and subscribe. Now, let's begin. The excitement around this telescope did not arrive suddenly. It gathered slowly, like a low hum beneath the noise of everyday news, until it became impossible to ignore, even without asking for it. The name James Webb Space Telescope seemed to find its way into conversations, headlines, and quiet moments of curiosity, not because it was loud, but because it promised something different, a deeper look, a gentler, farther-reaching eye than anything humanity had built before. This telescope is more powerful than any space telescope that came before it. Even the beloved Hubble, its size alone tells a story of ambition. It is so large that it could not travel into space in one piece. Instead, it was carefully folded in on itself, like a patient piece of cosmic origami, tucked into the narrow confines of a rocket fairing. Every fold mattered. Every hinge had a purpose. Once unfolded in space, it would become something vast and delicate at the same time. Its sensitivity is so extreme that warmth itself becomes an obstacle. Even the faint heat from its own instruments could overwhelm what it is meant to see. To prevent this, the telescope must remain only slightly warmer than absolute zero, a temperature so close to complete stillness that heat nearly disappears. In that deep cold, its sensors can listen to the faintest whispers of light arriving from unimaginably distant places. The cost of creating such an instrument reached $10 billion, but the true price was paid in time and patience. Decades passed as engineers, scientists, and technicians worked through problems that had never been solved before. At one point, there were more than 300 separate places where something could fail. Any single mistake could have ended the mission before it truly began. And yet, against those odds, it arrived. Its purpose is quietly profound. It studies planetary systems, searching for subtle signs that life might exist elsewhere. It examines how planets, stars, and galaxies form, not in theory, but in living detail, and it peers outward, far beyond our local neighborhood, toward objects so distant that the light they emit has been traveling almost as long as the universe itself has existed. In practical terms, this means looking back toward the first stars and the earliest galaxies, gathering light that began its journey near the beginning of time. Those first images have already started to arrive, carrying stories written in ancient photons. They are not dramatic in the way explosions are dramatic. They are dramatic in their patience, in how long they have waited to be seen. This telescope did not appear fully formed. Its story began decades earlier, in the 1990s, when it existed only as an idea. At that time, it was expected to cost about $1 billion and to launch in the year 2007. Reality as it often does, moved more slowly. Technical challenges stacked up, schedules slipped, expectations had to be reshaped again and again. It was not until December of the year 2021 that the telescope finally left Earth. Even then, its journey was only beginning. For months afterward, it carefully unfolded itself in space, step by step, activating systems, testing components, and slowly becoming whole, fully assembled. It weighs 6,500 kilograms. Its sun shield, stretching roughly 14 by 21 meters, spans an area comparable to a tennis court, catching sunlight and holding it back so the instruments can remain cold and calm. The mirror at its heart is vast, with a light collecting area 6 times larger than Hubble's. This allows it to gather more photons from farther away, producing images that feel both crisp and deep. Alongside the mirror are multiple cameras and scientific instruments designed to observe the universe primarily in infrared light. This choice defines its unique role as the universe expands. Light traveling across vast distances becomes stretched. No matter how that light began, over enough time, it shifts into infrared to see the most distant objects at all. An infrared telescope is essential. Infrared light also has another gift. It can pass through clouds of cosmic dust that block visible light, revealing regions that were previously hidden from view. Where Hubble saw shadows, James Webb sees structure, although it is often described as Hubble's successor. The relationship between the two telescopes is more cooperative than competitive. Hubble observes mostly visible and ultraviolet light. James Webb focuses almost entirely on infrared and cannot see some visible wavelengths at all. Together, they form a more complete picture, each filling in what the other cannot see. With this ability in mind, the view begins close to home, within our own galaxy. One of the first regions revealed is a dramatic landscape known as the Cosmic Cliffs, formerly called NGC 3324. This region lies within the Carina Nebula, about 7,600 light-years away. The towering shapes visible here rise roughly 7 light-years high. Sculpted by powerful stellar winds, what appears in view is only a small portion of a much larger structure. At the center of the nebula is a hollowed-out cavity, where intense winds from massive stars have pushed dust outward, clearing space around them. The cliffs mark the edge of this bubble, a boundary between emptiness and abundance. Scientists are drawn to this place because it captures star formation in action. Here, dust and gas are compressed and stirred by stellar winds, gathering into dense pockets where new stars can begin to form. Yet this process has remained elusive. Dust is both the raw material for stars and a veil that hides their earliest moments. It wraps forming stars in thick cocoons, blocking visible light and leaving crucial stages unseen. Infrared observation changes that. Using its mid-infrared instrument, James Webb can peel back these dusty layers and reveal what lies beneath. Compared to earlier images, the detail is striking. Filaments, cavities, and subtle temperature differences become visible. This single view will provide valuable insights into how stars are born for years to come. From birth, attention gently turns toward endings. A little closer to Earth lies NGC 3132, also known as the Southern Ring Nebula. This object is a planetary nebula, Though the name is misleading, it has nothing to do with planets. Early astronomers gave it that name because its rounded shape reminded them of planets through small telescopes. In reality, a planetary nebula forms when a star near the end of its life sheds its outer layers, releasing gas and dust into space. This material carries a chemical record of what the star was made of. Understanding that composition helps scientists learn what future generations of stars may inherit. Images from James Webb reveal this nebula in new depth. By comparing views from different infrared instruments, scientists can distinguish between cooler dust and warmer regions. Tracing how material flows outward, they have learned that one of the stars in this system has not yet fully reached its final stage, meaning another nebula may still form in the future. The interaction between the two stars stirs the surrounding material into intricate patterns, shaped by gravity and motion over long spans of time. Beyond the Milky Way, the view expands again. About 161,000 light-years away lies the Tarantula Nebula, named for its sprawling, web-like appearance. This region is remarkable not only for its beauty, but for what it represents. Conditions here resemble a period in cosmic history known as the Cosmic Noon, when star formation across the universe reached its peak. This era occurred roughly 1 billion years after the universe began, a time when galaxies were rapidly forming stars. In the Tarantula Nebula, James Webb can identify stars that are only just beginning to exist, offering a rare look at processes that were once common but are now less frequent. It is a living echo of a more active universe. As distance increases further, individual stars fade from view. Structures grow larger. Entire galaxies come into focus. One such arrangement is Stephan's Quintet, a group of 5 galaxies that appear close together from our perspective, though one is actually much farther away. 4 of them, however, are gravitationally bound and destined to interact. 2 are already colliding, their encounter heating dust to extreme temperatures. Infrared vision reveals glowing streams of material drawn outward by overwhelming gravitational forces. Energy released, not in moments, but across millions of years. What appears at first glance like chaos is, in truth, a slow and intricate cosmic dance. This view is not a single frozen instant, but the careful weaving together of nearly 1,000 separate exposures, layered patiently to uncover structure within the turbulence. And then the gaze drifts even farther, until distance itself begins to resist observation. In an image known as Webb's first deep field, the telescope rests its attention on a region of sky so small that a single grain of sand, held at arm's length, could hide it completely. Here, the familiar markers we rely on begin to fade. Individual stars no longer announce themselves. The scene feels quiet, almost empty at first, but as the eye settles, something subtle becomes clear. Those countless faint points scattered across the deep field are not stars at all. At these immense distances, stars are simply too small, too dim to stand alone in isolation. What fills the frame instead are entire galaxies, vast island universes suspended in darkness. Each tiny glow holds billions of stars bound together, wrapped in dust, shaped by gravity, carrying stories that have been unfolding for nearly the age of the universe itself. And in among them, you can notice something that feels almost like a dream of optics. gentle arcs, stretched smears, and curved slivers of light. They can resemble the soft bend you might see through a fisheye lens. Except this is not a camera trick. This is gravity itself, shaping what the light becomes by the time it reaches us. A nearer galaxy, heavy with mass, can act like a lens. It bends the path of light, coming from something far behind it, warping the background into loops and crescents. The universe, in this quiet way, begins to reveal its depth, not as a flat picture, but as layers foreground and background braided together by gravity. Somewhere in that crowded field, tucked among warmer colors and faint smudges, there is a galaxy so distant that the light leaving it near its birth has only now arrived at our telescopes. Finding it is not dramatic. It does not announce itself with brightness. It asks for patience and a closer look. So the view narrows, the image is enlarged, and there it is, small, reddish, easily missed if you didn't know to linger. It looks like almost nothing, a tiny ember floating in a black ocean. That reddish tone matters. When scientists study the light from a faraway galaxy, they look for familiar patterns, markers in the glow that match what we see in nearer objects. But distance stretches light. The expansion of the universe pulls those patterns toward longer wavelengths, sliding them away from where they would normally sit in visible light. By measuring how far those markers have shifted, how much the light has been redshifted, scientists can estimate how long that light has been traveling, and therefore how far away the galaxy is. For this small red dot, the estimate is breathtaking, about 13.1 billion light-years away. When you hold that number gently, the meaning settles in. If the universe is thought to be about 13.7 billion years old, then this galaxy is showing itself to us from a time close to the beginning, from an era when everything was younger, rawer, and still learning what it would become. It can feel a little disappointing at first, because it's so small. After all that distance, after all that time, it's just a speck. But that smallness is not failure. It's honesty. It's what the early universe looks like when it reaches us across nearly all of time. And there is also a quiet kind of hope in what this image suggests. If you compare the same patch of sky as seen by Hubble, you can feel the difference immediately. The James Webb view is sharper, richer, and filled with more objects. But the most important contrast is not only the clarity, it's the time it took to gather the light. Hubble created its deep view by staring at that tiny region for about 10 days, collecting photons slowly, building the picture piece by piece. James Webb created its own deep view in about half a day, about 12 hours. When you let that sink in, you realize what it implies. If the telescope can do this much in about 1/12 of the time, then with days of focus, days of patient watching, the detail could become even more extraordinary. That tiny red dot may not be the best James Webb can do. It may be only the beginning of what it can reveal when it is allowed to listen longer. For now, these first images are enough to change the feeling of what is possible. They show scientific breakthroughs on the horizon. Yes, but they also show a kind of beauty that doesn't need to shout. The universe, when seen with the right eyes, carries its own quiet artistry. Still, even with all this, patience remains part of the bargain. At this stage, the telescope has only just finished its careful calibrations. It has been letting its instruments settle into their working temperatures, letting systems stabilize, letting everything become as precise as it needs to be. And because the telescope's expected working life is limited, often described as something like 5 to 10 years' time on it, becomes precious. Every second is argued over, planned over, protected. Because every moment of observation can become a discovery someone has waited their whole career to make. In the years ahead, it will examine exoplanets, looking for signs that their atmospheres might be hospitable, subtle chemical hints that a world could be more than a barren rock. It will peel back nebulae again and again, watching stellar nurseries and the way dust collapses into new suns. And it will help clarify the difference between an old galaxy like ours and the very young galaxies that formed soon after the Big Bang, when structure was still assembling itself for the first time with an instrument this powerful. It's hard not to wonder what else is waiting. We can step outside at night and look up into the glittering dark, and it can feel profound, like standing on a shore and listening to waves you cannot see. But our view from the ground is softened and limited. Light pollution washes out the faint details. The atmosphere shimmers and distorts, bending starlight as it passes through moving air. And our eyes, as marvelous as they are, were never designed to read the faintest pages of the cosmos. That is why space telescopes matter, high above Earth. The Hubble Space Telescope has spent years orbiting at roughly 550 kilometers overhead, free from the blurring atmosphere, opening a clear window into deep space. It has reshaped astrophysics, refined our measurements, and offered images so clean and strange they feel like postcards from a place we never truly expected to touch. In that steady vantage point, Hubble has been able to gather light from far beyond what the naked eye could ever hold, and to turn it into views that make the universe feel both larger and more intimate at once. When you follow Hubble's gaze outward, it can feel like traveling quietly, steadily across enormous distances. One of the first remarkable encounters in that journey lies about 3,800 light-years away, where something like vast blue wings seems to stretch into space. The shape is so delicate and wide that it almost resembles a butterfly in flight, suspended forever in the dark. This is NGC 6302, often called the Butterfly Nebula. It lives within the Milky Way, and its luminous blues and turquoise tones come from glowing gas material that once belonged to a star's outer layers. Over time, that star shed its skin into space, and the gas expanded outward, shaping itself into sweeping lobes. The wing-like form traces a journey that has taken about 2,200 years, spreading material across more than 2 light-years. In more recent observations, astronomers have found extraordinary intricacy in the jets and bubbles erupting near the nebula's center. Details so fine, they suggest the shape is not fixed, but changing, sculpted by bursts and flows that shift the wings in subtle ways. A little farther out, at about 8,000 light-years, Hubble reveals a region that feels busier, more crowded with young brilliance. There is a star cluster known as Pismis 24, set within a broader landscape of glowing gas. Your attention is pulled first toward the bright core of the emission nebula, rising and shining like a soft ember cloud. Then you notice the stars scattered through and around it, many of them strikingly blue. Those blue stars earn their color from their intense heat. They burn far hotter than our sun. And one reason is mass. In general terms, the more massive a star is, the hotter and brighter it tends to be. And these blue stars can be at least 3 times the mass of our Sun. Their radiation is fierce, especially in ultraviolet, and it makes the surrounding gas heat and churn into complicated clouds. That same radiation, beautiful as it is, also makes the region difficult to study because it stirs and sculpts the material constantly, leaving a living fog of structure for a time. One object in this cluster, often referred to as Pismis 24-1, was thought to be almost unimaginably massive, close to 300 times the mass of the Sun. Later, with better resolution and analysis, it became more likely that this one star was actually a small system, at least 3 stars, each closer to about 100 solar masses, smaller than the first estimate, but still among the most massive stars ever recorded. Pismis 24 sits within the diffuse nebula NGC 6357, a true cosmic nursery. It contains protostars, stars in their earliest stage, still gathering mass from the molecular cloud around them. Nearby are many young stars wrapped in expanding cocoons of gas, which makes the whole region feel almost alive, as if it is breathing and growing in the dark. Farther still, at around 60,000 light-years, there is a globular cluster called Palomar 12. It hangs out near the outskirts of the Milky Way's halo, a compact swarm of stars traveling together. What makes it especially curious is its age. These stars appear to be about 30% younger than many other globular clusters associated with our galaxy. The reason for that youth is not a mystery of how they formed, but of where they came from. Palomar 12 was, in a sense, taken. It likely originated in the Sagittarius dwarf elliptical galaxy about 1.7 billion years ago. Tidal interactions with the Milky Way tore the cluster away from its home and pulled it into our galaxy's outskirts. Even now, that home galaxy is being stretched and disrupted as the Milky Way's gravity pulls at it. These tidal forces are usually most intense in the immediate neighborhoods of galaxies. But when galaxies pass near each other or collide, the results can be dramatic. Stars and clusters can be stripped, shapes can be distorted, and pieces of one galaxy can end up living inside another. Palomar 12 becomes a quiet example of how galaxies grow not only by making new stars, but by borrowing and taking, by absorbing what passes too close. And Hubble's reach does not stop there. With each new jump outward, the scale changes. Around 30 million light-years away, Hubble shows a familiar object from a striking angle, the Sombrero Galaxy, seen nearly edge-on. It displays the flat, disc-like shape that is common for many galaxies, a shape we don't always appreciate when we look at galaxies face-on. It's natural to wonder why so many galaxies are flat, when so many smaller objects, planets, moons, even many asteroids, tend to become roughly spherical. The difference is motion and rotation on enormous scales. As a galaxy forms, gravity pulls material inward, but the system also carries angular momentum. Over time, as the mass settles and rotates, often influenced by the deep gravitational presence at the center, the motion favors a flattened disk. With material spread out along a plane in the Sombrero Galaxy, that structure becomes especially vivid, a brilliant, almost blinding white core. and distinct lanes of dark dust, spiraling and curving outward. The dust is most pronounced along the rim, creating the visual impression of a wide-brimmed hat floating in space at around 65 million light-years. Another galaxy appears with a very different personality, NGC 1052-DF2. Its texture is diffuse, so spread out and faint that you can see more distant galaxies behind it, as though it were made of mist instead of stars. That translucence gives it an almost ghostly appearance. But the strangest suggestion about this galaxy is not how it looks. It is the possibility that it contains very little, or perhaps almost none, of the dark matter that galaxies are usually thought to be wrapped in. It was among the first galaxies discussed in this way, an object that seemed to behave as if the unseen mass were missing. And if that interpretation holds, it raises a quiet discomfort in the mind. Because dark matter is often used to explain why galaxies rotate the way they do, why clusters hold together the way they do. As for why this galaxy might be different, there is still uncertainty. Sometimes the universe does not answer immediately. Sometimes it simply presents the puzzle and waits. From there, the view expands again to scales where galaxies gather like cities. Just over 300 million light-years away lies the Coma Cluster, a vast assembly of more than 1,000 galaxies bound together by gravity. It is also historically important, because clusters like this were among the first places where astronomers found strong indications that dark matter might exist. The visible matter, the stars and gas, did not seem to provide enough gravity to explain what the cluster was doing. Something else appeared to be holding it together. In images of the Coma Cluster, you can also find countless intracluster globular clusters, spherical groups of stars that are not bound to any single galaxy, but to the cluster's gravitational field itself. They drift in the space between galaxies, like lanterns floating in a wide valley, loyal not to one home, but to the larger structure that contains them. And even that is not the edge. Hubble can reach farther, to the point where individual stars, single stars, not whole galaxies, become miracles to detect at all. Over 9 billion light-years away, there is an object known as MACSJ 1149. And within the lensing effects of that distant cluster, a star once stood out in a way that seemed almost impossible. It became known by the nickname Icarus. For a time, it was the most distant individual star we knew of. The light from it takes so long to reach us that we see it as it was when the universe was only about 30% of its current age, an earlier cosmos. Still young, still forming its grandest structures, and to hold the distance in your mind with something more tangible. Consider this: when it was captured in that image, Icarus was at least 100 times farther away than the nearest star. And still, even after a star like Icarus has managed to reach us across that immense gulf, the universe keeps offering deeper distances, places that feel less like far away and more like long ago. There is another star, glimpsed through Hubble's patient eye, with a nickname that sounds like a small piece of dawn, Arundel. Catalogued as WHL0137-LS, it appears in the direction of the Cetus cluster, and its light has been traveling for more than 12.9 billion years before it touched our instruments. That does not mean it is simply 12.9 billion light-years away in a straightforward, frozen sense. Space has not held still while the light traveled. The universe has been expanding the entire time, gently stretching the separation between us and the source. So, when astronomers describe where Arundel is in today's expanded cosmos, the number grows larger, closer to 28 billion light-years. It is a soft, unsettling kind of distance, because it reminds you that what you're seeing is not a place you could ever point to in the present tense. You are seeing where it was, almost 13 billion years ago, preserved in a thin thread of ancient light. Even with that distance, Arundel seems unusually large. Estimates suggest it may be somewhere between 50 and 100 times the size of our Sun. A star built on that scale does not live gently. Its mass drives it to burn bright and fast. And that same power makes its ending dramatic. From our perspective, it is expected to explode as a supernova in a few million years, an event that, out there, may already have happened long ago, but whose news will not reach us for an unimaginably long time. Its name carries a quiet, human tenderness. Arundel connects to an Old English term often associated with a morning star or a rising light, and it also echoes a reference from J.R.R. Tolkien's stories, an image of a figure who traveled the sky carrying a jewel bright as a star. It's the kind of name people give when an object feels too distant to hold, without a little poetry. Beyond the nickname and the size, the star is also fiercely hot. Its effective surface temperature is thought to be at least 20,000 Kelvin, almost 4 times hotter than our Sun. That heat shifts much of its brilliance into ultraviolet light, the kind our eyes cannot see, but which carries clear fingerprints of what the star is made of and how it shines. There is even a small possibility that Arundel could be what astronomers call a population 3 star, an early kind of star that would contain almost no elements beyond hydrogen and helium. In the young universe, heavier elements were rare. They had not yet been forged in large quantities and scattered by countless supernovae. A true population 3 star would be a relic from that first era of starlight, expected to be far more luminous than the familiar stars of later cosmic generations. It's an intoxicating thought, but it remains only a possibility, because the evidence at these distances is always thin. The farther you look, the fewer photons you have to work with, and the more careful you must be about what you claim. So how can Hubble see a single star at such a distance at all? It comes back to the same quiet bending of light that makes the deep field feel layered, as though space has depth you can almost touch. Arundel is visible because of gravitational lensing. A massive cluster of galaxies sits in the right place along our line of sight, and its combined gravity warps space-time enough to bend and magnify the star's light in just the right alignment. The cluster acts like a colossal lens, focusing faint light that would otherwise slip past us unnoticed. It is not that Hubble suddenly became larger. It is that the universe itself, for a moment, helped Hubble see farther than it could on its own. And by this point, the sense of distance becomes almost tenderly absurd. Everything is so far away that even Hubble, magnificent as it is, begins to press against its limits. The images become less like portraits and more like hints, soft, red embers on black velvet, signals that ask for patience rather than certainty. Even so, there is one more object Hubble can show us. At the far edge of this outward gaze, a red-shifted galaxy candidate known as HD1 It is often described as among the earliest and most distant known objects in the observable universe. To our eyes, it is little more than a faint red dot, barely there, as if someone touched the darkness with the smallest brush of color. That faintness hides an enormous scale. The light from HD1 began its journey about 13.5 billion years ago. That is how long the message has been traveling. But because of cosmic expansion, its present-day distance is described as even greater, estimated around 33.4 billion light-years, once the stretching of space is taken into account. It sits at the very edge of what we can currently claim to perceive, balanced on the boundary between seen and inferred. Even at that edge, the little dot carries clues. Its ultraviolet emissions appear extremely luminous, which hints that it could be a starburst galaxy, one forming stars at a rate far beyond what we see in calmer, mature galaxies. Another possibility is that it could host those immense population 3 stars early, brilliant giants whose light would be unusually intense compared to the stars we know nearby. But all of these ideas remain speculative, not because scientists are careless, but because the signal is so faint. When you are working with so few photons, every interpretation has to be held lightly. What can be said with confidence is simpler, and in a strange way, more moving. Something is out there at that extreme distance, sending us light that has been traveling since near the beginning. For now, that is the farthest thing we can see. To learn more, and perhaps to push even farther, we need an instrument built for the oldest light, an infrared eye, powerful enough to catch what the expansion of the universe has stretched beyond visible reach. That is the realm where the James Webb Space Telescope becomes essential. Until then, there is a quiet gratitude in what Hubble has already allowed, a journey spanning roughly 33 billion light-years in today's expanded measure, carried on a thread of ancient light. And after a journey like that, the mind sometimes wants to return home, not because home is small, but because home is where distance becomes touchable again, beyond Neptune. In the dark, frigid, outer quiet of our own solar system, there is another frontier, not made of galaxies, but of ice and debris, ancient remnants left behind from the solar system's birth, drifting in slow silence, preserved by deep cold. To reach that shadowed region in imagination, you pass the rocky inner worlds, glide by Mars, and move outward past Jupiter and Saturn with their swirling storms. Farther still, beyond Uranus and Neptune, the sunlight thins until it feels like a memory rather than a warmth. And there, encircling our system like a frozen halo, is the Kuiper Belt. It is not simply a collection of distant rocks. It is a time capsule from about 4.6 billion years ago, holding building blocks from the early solar system material that never quite gathered into a full-sized planet. Within this region live several dwarf planets and countless smaller bodies, many of them strange enough to keep astronomers quietly puzzled for years. For a long time, this belt was only an idea, before anyone knew for certain it was real. Astronomers suspected that something must exist beyond Neptune. Pluto, for decades, was treated as an isolated wanderer in the outer solar system, a solitary object on an unusual path. But its small size and its odd orbit made it feel less like a lone planet and more like a hint, like a member of a larger family we simply hadn't found yet. In the year 1951, astronomer Gerard Kuiper predicted that a belt of icy objects might exist just beyond Neptune's orbit. It was a powerful suspicion. But the objects would be faint, distant, and difficult to detect with the telescopes available at the time. So the idea remained theoretical for decades, present in papers and conversations, but not yet pinned to a confirmed discovery. That changed in the year 1992, when astronomers David Jewett and Jane Liu discovered the first confirmed Kuiper Belt object, known as 1992 QB1. With that one finding, the outer solar system felt less empty. Pluto and its large moon Charon had been discovered earlier. Pluto in the year 1930 and Charon in the year 1978. But after 1992, QB1. These familiar bodies were understood differently. They could be seen as part of a broader population, and in the years since, thousands more Kuiper Belt objects have been identified, slowly filling in the map of that distant realm. To picture where the Kuiper Belt sits, it helps to imagine a steady outward journey from the Sun. Comparing it to other structures along the way, close in, you pass Mercury, Venus, Earth, and Mars. Between Mars and Jupiter lies the asteroid belt, a thin, spread out ring of rocky debris left over from the formation of the planets. It stretches roughly from about 2.2 to 3.2 astronomical units from the Sun and is about 1 astronomical unit wide. An astronomical unit is simply the average distance from the Sun to Earth. The asteroid belt contains objects of many sizes, from the largest asteroid, Vesta, about 525 kilometers wide, nearly the distance from London to Belfast, to far smaller bodies, some only tens of kilometers across. Yet even with all that material scattered across a wide region, the total mass of the entire asteroid belt combined is only about 3% of the mass of Earth's moon. It sounds like a lot until you realize how much space there is between everything. Beyond the asteroid belt, you enter the realm of the giants Jupiter, Saturn, Uranus, and Neptune. These worlds dominate the outer solar system with their gravity. And then, as you pass Neptune's orbit at about 30 astronomical units, you arrive at an even more remote frontier, the Kuiper Belt itself. This region extends roughly from 30 to 50 astronomical units from the Sun. It contains frozen relics of the early solar system. Dwarf planets such as Pluto, Haumea, Eris, and Makemake, and countless other smaller bodies, like the asteroid belt. It is made of ancient debris, but unlike the asteroid belt, which is mostly rocky, the Kuiper Belt is rich in ice's water ice, ammonia ice, and frozen methane, forming a thicker, donut-shaped ring of debris. Kuiper Belt objects are considered among the oldest surviving pieces of the solar nebula, the original cloud of gas and dust that formed the planets. In a very distant past, some of those pieces might have been able to come together into something larger, but Neptune's gravity kept stirring the region, preventing the icy bodies from calmly coalescing into a new planet. The result is what we see today, a wide, scattered archive rather than a single finished world. The Kuiper Belt likely contains hundreds of thousands of large icy bodies bigger than 100 kilometers across, along with vast numbers of comets and smaller debris. The spacing is one of the hardest things to truly feel. On average, Objects can be separated by something like 0.02 to 0.1 astronomical unit distances that can be imagined as roughly 10 million kilometers between neighbors. In that dim outer quiet, they drift in near silence, preserving clues about how planets formed and how comets are made. And even that is not the far edge of the Kuiper population. Overlapping the outer part of the main belt is the scattered disk, a region that extends outward toward nearly 1,000 astronomical units, with some objects on orbits that carry them even farther. Compared to the asteroid belt, the Kuiper belt is vastly more expansive, stretching across a much larger volume of space. Beyond these belts, there is also the Oort cloud, an immense spherical swarm of icy debris believed to encircle the solar system. It is so distant that even our most powerful telescopes cannot see it directly. One way to feel the difference is distance and shape. The Kuiper belt is thousands of times closer to the Sun than the theorized center of the Oort cloud, which is often described as stretching from about 2,000 to 100,000 astronomical units. The Kuiper belt is donut-shaped, concentrated near the plane of the planets, while the Oort cloud is spherical, like a gigantic bubble of swarming debris. What they share is their role as comet reservoirs. The Oort cloud is thought to supply many long-period comets, while the Kuiper belt is where many short-period comets are born, comets with orbits of less than 200 years. And even the Kuiper belt we see today is only a fraction of what it once was. Long ago, it may have held something like 7 to 10 times the mass of Earth. Over time, the shifting orbits of the 4 giant gas and ice planets scattered much of that mass away. What remains is no more than about 10% of Earth's mass. And even that continues to erode. Collisions occasionally break objects apart, leaving smaller fragments behind. Some of the resulting dust is pushed out of the solar system by the solar wind. Sometimes, collisions or Neptune's gravity nudge Kuiper belt objects onto new paths toward the Sun, creating those short-period comets as they approach the inner solar system. Sunlight drives them to shed material, building the spectacular tails we can see from Earth. Several famous comets are associated with the Kuiper belt or its scattered disk, including Halley's Comet, with an average orbital period of 76 Earth years, and Comet Shoemaker-Levy 9, which broke apart and crashed into Jupiter in the year 1994. In the first ever observed collision of 2 solar system bodies, Jupiter endured. Of course, but the impact did not pass unnoticed. Even from Earth, people could see the scars, dark bruises blooming across a world that usually looks untouchable. It was one of those rare reminders that the solar system is not a still life. It's a living place, where gravity arranges meetings we would never choose, and where even a giant can be marked for a time. You may have also heard recent chatter about a near-Earth asteroid called 2024 Y4. The odds of anything dramatic are very small, an even smaller chance of an impact with Earth, and a slightly different sliver of possibility involving the Moon. But the short-period comets that trace their origins back to the Kuiper belt are not an immediate worry for us in the next 100 years or more. In other words, this vast, frozen frontier can stay what it's always been for us: mysterious, distant, and quietly fascinating, rather than threatening. And even though the Kuiper belt is only a remnant of what it once was, it still feels endless when you imagine it properly. An archive of icy bodies drifting in slow, dark orbits, each one holding some small clue about how the solar system learned to take shape. For a long time, most of what we knew came from faraway ground-based telescopes peering through Earth's atmosphere. And Hubble, looking down from space with its clear, steady eye. But there is one spacecraft that actually went there, one that crossed that outer quiet and looked back with its own cameras. NASA's New Horizons is, so far, the only spacecraft to have truly visited the Kuiper Belt. It is best known for its flyby of Pluto. But it also reached another Kuiper Belt object, originally labeled 2014 MU69, later given an official name Arakoth, a word meaning sky in a Native American Powhatan or Algonquian language. New Horizons met Arakoth in the year 2019, in the most distant flyby in the history of space exploration, about 1.5 billion kilometers beyond Pluto. At closest approach, the spacecraft passed roughly 3,500 kilometers above the surface, and even among the Kuiper Belt's many quiet mysteries, Arakoth still managed to surprise everyone. Its shape was unlike anything we'd ever seen up close in our solar system. Arakoth is a small, icy body known as a contact binary, two distinct lobes that gently merged into a single object. From certain angles, it resembles a flattened snowman, or two rounded forms pressed together and smoothed by time. It measures only about 35 kilometers long, about 20 kilometers wide, and about 10 kilometers thick. On paper, that can sound too small to matter, but in the Kuiper Belt, smallness can be an advantage. Small bodies are often less altered, less reworked by heat and violent geology. They can preserve the original textures of early formation. Arakoth doesn't have an atmosphere. It doesn't have the kind of dramatic mountains and volcanoes that catch the imagination in a single glance. Instead, it offers something subtler structure. The strange, pancake-like snowman shape carries information about how the earliest building blocks of planets came together. Even its gravity field and rotation feel a little counterintuitive when you picture how such a shape should behave. And that oddness is part of the gift. It's a clue written in the object's very body. After the flyby, papers began to accumulate careful studies of Arakoth's geology, geophysics, composition, and likely history. And out of that slow, thoughtful work came something close to an answer for a long-running debate about how planetesimals form. Planetesimals are the stepping stones of planet-making small objects that gather and combine into larger bodies, which may eventually build something planet-sized if conditions allow. For years, two broad ideas competed. One was hierarchical accretion, the notion that small objects would slam into each other at relatively high speeds, fragmenting and reassembling over time, gradually building something bigger through repeated collisions. The other was local cloud collapse, the idea that nearby material in a region could collapse together more gently under gravity, forming larger bodies without the same violent, high-speed impacts. Arakoth seems to favor the gentler story. Its smooth surface, and the lack of deep fractures that would suggest intense stress, point toward formation at low speed, more like a soft meeting than a crash. The evidence became strong enough that mission scientists spoke with unusual confidence about what it meant. The Kuiper Belt, in its quiet way, helped settle a multi-decade argument about the earliest steps of planet formation. Local cloud collapse appears to be the better explanation for how these first building blocks can come together. And then, of course, New Horizons gave us Pluto, the most familiar name in the Kuiper Belt. And yet, before that flyby, still mostly a blur at the edge of sunlight, in the year 2015, the spacecraft passed close enough to make Pluto feel almost nearby. It collected observations not only of Pluto, but also of its largest moon, Charon, and it gathered data on Pluto's other small satellites, Nix, Hydra, Kerberos, and Styx. Suddenly, what had once been a distant point of light became a world with weather, textures, and history. Nearly everyone remembers the heart-shaped bright region on Pluto's surface, often called Tombaugh Regio. It looks gentle, almost friendly, like a signature left by chance. But there's more going on there than a simple pattern of light and dark. The heart includes a vast, bright western lobe known as Sputnik Planitia, named after Earth's first artificial satellite, Sputnik 1. This region is understood as a glacier, a broad plain of frozen nitrogen, an icy sea that behaves like slow-moving fluid over long timescales. It spans roughly 1,000 kilometers across and may be about 4 kilometers deep, making it a strong candidate for the largest known glacier in the solar system. The eastern lobe of the heart appears bright. For a related reason, nitrogen carried from Sputnik Planitia can be deposited elsewhere as ice, painting nearby terrain in paler tones. So the heart is not merely a pretty mark. It is an active clue about how Pluto moves heat, how it cycles volatile ices, and how its surface renews itself. New Horizons changed Pluto's personality in our minds. It revealed a world far more complex than many expected, a place with landscapes that look young in some regions, ancient in others, and with processes that still shape the surface even so far from the sun. That complexity naturally raised deeper questions, especially about why the heart exists at all. Some interpretations suggested that an internal ocean of water ice hidden beneath the surface could help explain the region's structure and behavior. But another idea has grown more persuasive, that the heart may have begun with a low-velocity impact, one that left a gigantic splatter across Pluto's surface, forming much of the western half of the heart shape. The impact is imagined not as a straight-on hit, but an oblique one, angled, skimming in a way that spreads material. A simple image helps, like throwing a water balloon across dry pavement, the way you might skip a stone across a pond. When the balloon scrapes along at an angle, it bursts and smears, leaving an elongated splash. In this gentler, icy, planetary version, a similar kind of angled, low-speed collision could have shaped the broad outline of Pluto's bright western lobe. And Pluto wasn't the only marvel. Charon, too, stepped out of the darkness with unexpected detail. In images, you can make out a vast tectonic belt running around its equator, an enormous system of fractures and ridges. That kind of global structure suggests Charon may once have had a water-ice ocean inside it, long gone now, but remembered in the stretching and cracking of the crust as the interior evolved. All of this leaves a quiet, lingering question: what comes next for the Kuiper Belt? And for our understanding of the solar system's outermost history, New Horizons continues onward, and it is expected to exit the Kuiper Belt sometime between the year 2028 and the year 2029. There is no confirmed target for another flyby at the moment, but the possibility remains. that a suitable object could be found. Instruments like the James Webb Space Telescope can help analyze the composition of Kuiper Belt objects from afar, teasing out the chemistry of their surfaces by the way they reflect and emit infrared light. And farther ahead, more distant in time, as well as space, it's possible to imagine robotic missions that do more than pass by, missions that could land on one of these icy bodies, or even collect material for a return to Earth. The Kuiper Belt holds enough worlds for exploration to feel almost endless, one frozen relic at a time. And then, in the background of all these newer journeys, there's a quiet irony that deep space loves to keep. Some of the most powerful insights at the edge of our solar system are not coming from brand new, cutting-edge machines, but from old ones, machines built so long ago that their design belongs to another era of human life. In the year 1977, two pioneers left Earth on what may be one of the most epic explorations ever attempted. Their goal was to unravel the larger mystery of the solar system and our place within it. They gave us some of the first and best imagery of the outer planets. And they keep sending information even now from interstellar space about 47 years later, and roughly 24 billion kilometers farther on. Voyager 1 and Voyager 2 are more than circuitry and instruments. They became symbols curious, audacious, resilient. They didn't just deliver photographs of gas giants and their moons. They shaped the imagination of generations watching from Earth, widening the solar system in the human mind. These are still the farthest traveling human-made objects, trailblazers moving beyond the comfortable reach of home, carrying their small stores of power and memory into a place where sunlight is weak and radio signals grow thin. When people who worked on Voyager look back, what often stands out is how much the missions changed the baseline of knowledge. How many discoveries were not even guessed at before the probes arrived. The project scientist Edward Stone once reflected on that feeling. When you look back, you realize how little we actually knew before Voyager, and how often the mission revealed something no one expected to find. There is another layer to the irony. 2. Voyager's onboard computer has less memory than the one inside a modern car key fob, and the probes still rely on magnetic tape technology that traces back to the 1970s. In a world where electronics change every few years, these machines are older than many of the people listening now. And yet they keep functioning quietly, stubbornly far beyond what they were built to do. This is one of the conundrums of deep space exploration. Distances are so large, and travel times so long, that technology can become antiquated long before it reaches its most ambitious targets. Voyager 1 and Voyager 2 were not originally meant to travel all the way into interstellar space. They were designed for a 5-year mission to explore Jupiter and Saturn and their larger moons, made possible by a rare planetary alignment that comes around roughly once every 176 years. After those initial objectives were met, the mission grew. A flyby of Uranus and Neptune was added for one of the probes, and later those goals were completed as well. Eventually, NASA announced an even more ambitious extension, the Voyager interstellar mission, meant to explore the outer limits of the Sun's sphere of influence and beyond. That final journey would take both probes away from the main planetary plane, out toward regions like the termination shock, into the denser, hotter heliosheath, and finally across the heliopause into interstellar space. How did these remarkable machines manage to accomplish so much beyond the scope of their original mission? It all comes down to that old, but incredibly effective technology. It really did come down to old technology, used with a kind of quiet boldness. NASA's engineers made choices that weren't just clever for the moment, but kind to the future. The probes weren't built to impress on day one. They were built to endure. One of the most important decisions was the fuel source. Each Voyager carries a long-lasting radioisotope thermoelectric generator, a device that turns the heat from decaying plutonium-238 into electrical power. At launch, each generator could produce about 157 watts of electricity, roughly enough to run a laptop and maybe top up a phone. It sounds modest, almost quaint, but it was more than the spacecraft needed at the start. And more importantly, it didn't depend on sunlight. Out where sunlight thins into something weak and watery that matters, the trade-off is that the power slowly declines over time. With a half-life of about 87.7 years, even so, it was enough to keep essential systems alive well into the 2020s. That long-range thinking was no accident, because when Voyager 1 and Voyager 2 launched in the year 1977, NASA knew a rare door was about to open. The outer planets were approaching an alignment that comes around roughly once every 176 years. The last time it happened, it was the age of Napoleon's first reign, another world entirely, with no radios, no rockets, no idea that tiny machines would one day slip between planets. This alignment meant something beautiful for navigation. With carefully chosen paths, the probes could visit multiple outer planets with minimal course correction, borrowing speed through gravity assists. Each close pass by a giant planet could sling the spacecraft onward faster than its rocket alone ever could. The concept wasn't entirely new. Pioneer missions had begun to prove it, but Voyager would depend on it in a way that felt daring at the time. The problem was time. The window was narrow, and there wasn't room to plan a neat line of follow-up missions if something went wrong. Funding was also uncertain. Congress would not commit to the full Grand Tour vision NASA had once hoped for, so the team did what explorers often do. They built for more than they were promised, and trusted that the results would earn their continuation. Each Voyager probe carries 11 scientific instruments. Many critical systems have redundancies backup modes that can be switched on if the primary hardware fails, and switched off again to conserve power when every watt begins to matter. To hold their orientation and adjust their course, the probes rely on gyroscopes and reference sensors, along with 16 hydrazine thrusters, including 8 backups. Those backups turned out not to be a luxury, but a lifeline. Voyager 2's main thrusters stopped working after about 37 years, and its backup thrusters, after decades of waiting in silence, were asked to wake up and do the job. They responded beautifully. That kind of reliability doesn't happen by luck. It happens because someone, long ago, imagined the day when the probe would be too far away for help. The computers on board were custom-built, ancient by today's standards, but cutting-edge in the year 1977. The wide-angle and narrow-angle cameras were managed by a command computer that carried fixed routines for fault detection and correction, like a small set of instincts built into the machine. But one computer mattered in a particularly intimate way: the attitude and articulation control subsystem. Attitude sounds like personality, but here it means orientation, how the spacecraft is pointed in space. Without careful attitude control, the high-gain antenna would drift off target, and the probe would lose its thin thread of connection to Earth. That connection is delicate. The transmitters on Voyager have power comparable to a refrigerator light bulb, and by the time the signal reaches Earth, it has spread and faded into something almost ghostly. To receive it, NASA uses the Deep Space Network, listening with enormous radio antennas that need to know where to aim with extraordinary precision. Otherwise, the probes could be lost like a needle in a haystack, measured not in miles, but in hundreds of billions of kilometers. Each Voyager carries a large dish antenna about 3.7 meters across for real-time transmission. It also carries an 8-track digital tape recorder that can buffer about 536 megabits for later enough to store around 100 photographs. Even at the time, it was a meaningful step up from the earlier Pioneer probes, which had no onboard data storage at all. And despite how primitive it sounds now, the tape recorders were built to last. The manufacturer claimed they could run thousands of kilometers of tape with no visible wear. They were tested for environments no one could truly recreate: cold, radiation, vibration, the long loneliness of mechanical work done in deep space. For years, they performed without data loss or failure, until they were eventually taken offline simply to conserve power. Durability was the quiet obsession behind everything. Before reaching Jupiter, both Voyagers had to pass through the asteroid belt, and earlier fears lingered that this region might shred a spacecraft like a hailstorm. Pioneer 10 and Pioneer 11 had already shown the belt was mostly empty space, which gave the Voyager team confidence. But the risk still felt real because one unlucky hit could have ended the story before it began. Both probes passed through unharmed, and the emptiness of that region became part of what they confirmed for us. Even after success piled on success, one worry remained cold. What would happen when the probes left the warm influence of the inner solar system and entered the deeper freeze beyond? NASA equipped them with multiple heaters to keep machinery within safe operating temperatures. But as power slowly waned, difficult choices had to be made. Some heaters were switched off to save energy. When the heater for the cosmic ray detector was turned off, its temperature dropped by 70 degrees Celsius. No repair team could ever be sent tens of billions of kilometers out to fix a frozen instrument. Everyone expected failure, but the detector kept working, steady and calm, as if the machine itself had learned how to endure the cold. That is part of why the Voyagers feel almost alive in our imagination. After about 45 years, their continued operation is less like a technical fact and more like a quiet testament. And then there's the story of what they actually saw, how the solar system looked when a human-made eye arrived close enough to make it feel real. On the 20th of August, in the year 1977, Voyager 2 launched from Cape Canaveral in Florida. Voyager 1 followed 2 weeks later, on the 5th of September. Even though both were bound for Jupiter, Voyager 1 was put on a shorter, faster trajectory, so launching second still allowed it to arrive first. It overtook Voyager 2 on the 15th of December in the year 1977 and exited the asteroid belt ahead of it, like a younger sibling taking a slightly quicker path through the dark. Not long after launch, Voyager 1 sent home a photograph 13 days later. From about 11.6 million kilometers away, it's a tender kind of image to begin with. Earth and its moon together in the distance. Small and bright against black, it can echo the feeling of the Earthrise photograph from Apollo 8. Taken 8 years earlier, this reminder that home can become a point of light astonishingly quickly. Knowing how far the probe would go after that makes the picture feel almost haunting. Like the first page of a book written in silence, Jupiter was the first great destination. And even at Voyager's speed, it took time. The giant planet sits about 714 million kilometers from the Sun's neighborhood we call home. Voyager 1 arrived first on the 5th of March in the year 1979. Voyager 2, despite leaving earlier, arrived 4 months later. On the 9th of July, Voyager 1's pace was about 17 kilometers per second, roughly 2 kilometers per second faster than Voyager 2. And its chosen trajectory helped it gain more speed relative to the Sun along the way. Voyager was not the first visitor to Jupiter. Pioneer 10 had passed by in the year 1972, 7 years earlier, and it brought valuable science. But Voyager brought something else, to vividness. It returned images that felt almost impossible, so richly textured, they can seem like paintings, even when you know they are photographs. In some of those frames, you can even pick out moons nearby Io and Europa, small companions riding beside a planet that seems too large to be real. Voyager 1 also recorded its approach in a way that let people feel the motion photographs taken at regular intervals, about every 10 hours, roughly 1 Jupiter day. So the planet's rotation would match from frame to frame. 66 images were stitched together into a time-lapse sequence, spanning from the 6th of January to the 3rd of February in the year 1979, covering about 27 million kilometers of closing distance. The effect is strangely hypnotic Jupiter swelling in the frame, a world growing larger without ever hurrying. When scientists looked closely, one thing stood out immediately: Jupiter's atmosphere was far more alive than expected. They anticipated layered winds moving in different directions across different bands. But what surprised them was the sheer turbulence plumes, eddies, and complex rotational patterns made stark and clear. The Great Red Spot, already suspected to be a counterclockwise rotating storm, was confirmed as such, and Voyager showed that it wasn't alone. The planet's clouds were filled with other storms and bright ovals, including a striking white spot below the Great Red Spot, evidence that Jupiter's atmosphere is not a neat set of stripes, but a restless ocean of motion. And then there was another revelation, softer but just as important. When we think of rings, we tend to think of Saturn, but scientists had suspected Jupiter might have rings too. Based on earlier hints, Voyager did more than confirm it. It provided the first images, showing that even Jupiter wears a faint, subtle system of rings, quiet arcs of material, circling a giant world that, until then, many of us had never truly seen. As Voyager drifted away from Jupiter, one last image lingered, a thin, glowing orange line stretching from the planet's edge. That faint line was Jupiter's ring system, catching sunlight at just the right angle, revealed most clearly as the spacecraft turned its back and continued onward. It felt like a quiet farewell, the giant world receding behind, still holding surprises even as it slipped into the dark. Before leaving Jupiter completely, attention gently returned to 2 of its moons, Io and Europa. What Voyager found there would ripple through planetary science for decades. Before these encounters, many geologists expected Io to resemble our own moon, old, quiet, and scarred by countless impact craters. But when the images arrived, that expectation quietly collapsed. The circular markings on Io were not craters at all. Dark patches dotted the surface, marking volcanic hotspots and vast lava lakes. Some lava flows were younger than 1 million years old, an eye blink on cosmic timescales. Io was alive. Today, Io is known as the most geologically active body in the entire solar system. At the time, seeing this was astonishing. Voyager even caught enormous eruptions in progress, towering plumes that hurled gas and material nearly 100 kilometers into space. Blue-tinted explosions blossomed above the surface, then faded, only for others to follow. These volcanoes erupt relentlessly, sometimes every few hours, turning what was expected to be a dead moon into a world of constant renewal and destruction. Just beyond Io's orbit lies Europa, and the contrast could not be more striking. Where Io is fire and motion, Europa is ice and quiet tension. Voyager 1 was the first to show Europa's surface clearly, revealing it crisscrossed with long, dark lines, scratches etched across a bright shell. Scientists suspected these markings were fractures in the ice, created by forces pulling and flexing the moon. Voyager's data also planted a radical idea beneath that icy crust. There might be a vast, swirling ocean of liquid water. At the time, it was only a suggestion. Today, it is one of the most compelling possibilities in planetary science. Jupiter itself also grew more crowded in Voyager's wake. Today, we know of 95 moons orbiting the giant planet. But before the year 1979, only 13 were known. Voyager discovered 3 more: Thebe, Matisse, and Adrastea, raising the total to 16 by the early 1980s. They were too small and faint to be photographed clearly at the time, but their discovery alone reshaped the map of the Jovian system. From Jupiter, the path curved onward to Saturn. After about 21 months of travel, Voyager 1 approached the ringed planet in November of the year 1980, with Voyager 2 following 9 months later. In August of the year 1981, Saturn had always been synonymous with rings. But Voyager revealed that those rings were far more intricate than anyone had imagined. Instead of a handful of broad bands, the rings resolved into hundreds of narrow ringlets, each one a delicate structure and motion. Voyager's close approach provided extraordinary detail. It discovered an entirely new ring, the G ring, and clarified the nature of the F ring, which had only recently been hinted at by earlier missions. Voyager showed that the F ring was kinked and braided, made of multiple strands rather than a single clean band. Nestled alongside it were 2 small moons, Prometheus and Pandora. These shepherd moons confirmed a long-held theory. Narrow rings are kept in place by nearby moons, whose gravity gently corrals the ring material, preventing it from spreading out and disappearing. Other features were more mysterious. In Saturn's B ring, Voyager revealed ghostly, spoke-like patterns broad, shadowy streaks that seemed to rotate with the planet. Their existence unsettled scientists because they did not fit neatly into models based purely on gravity. Even now, their origin is not fully understood, though the leading ideas involve electrostatic forces lifting tiny dust particles above the ring plane. Saturn's rings, it turned out, were not just sculpted by gravity, but by electricity as well. There was also a quieter, more sobering lesson. Voyager's measurements suggested that Saturn's rings are not permanent. Gravity slowly pulls ring material down into the planet, creating a kind of icy rain. If that process continues, Saturn's rings could fade away in roughly 300 million years. The most beautiful adornment in the solar system may be temporary. The flood of questions raised by Voyager eventually led to a dedicated mission, Cassini, launched in the year 1997, which orbited Saturn for 13 years and transformed our understanding of the planet and its moons. But even before Cassini, Voyager delivered decisive breakthroughs about Saturn's satellites. At the time, 14 moons were known. Voyager added 3 more, bringing the total to 17. 2 moons in particular stood out. Titan, Saturn's largest moon, had already been glimpsed by Pioneer 11. But Voyager revealed its true nature. Titan possesses a thick, nitrogen-rich atmosphere, the only moon in the solar system with one, and the only place beyond Earth where such an atmosphere exists. Its surface was hidden beneath hazy clouds, but the chemistry hinted at processes that felt oddly familiar. Enceladus was even more surprising. In images where Saturn loomed large in the foreground, Enceladus appeared small and distant, and yet something was clearly happening. The moon was erupting. Plumes of water vapor shot into space, hundreds of kilograms per second, rising as high as 10,000 kilometers, about 20 times Enceladus's own diameter. As the moon orbits Saturn, these repeated eruptions create a donut-shaped cloud of material that feeds one of Saturn's icy rings. Voyager hinted at this extraordinary activity. Cassini later confirmed it beyond doubt. Geologically, Enceladus revealed a split personality. One hemisphere looked young and smooth, almost freshly resurfaced. The other was ancient and battered, dense with impact craters. This contrast showed that Enceladus is not a frozen relic, but an active world, reshaping itself even in the deep cold far from the sun. After Saturn, the paths of the 2 Voyagers diverged. Voyager 1's close encounter with Titan bent its trajectory upward, out of the flat plane of the planets. From that moment on, it was aimed toward interstellar space. It would take another 32 years to get there, but its course was set. Voyager 2, meanwhile, used Saturn's gravity differently, slingshotting onward toward Uranus and Neptune worlds that had never been visited before and have not been visited since. These would become the first and only close flybys of those distant giants. 5 years after Saturn, Voyager 2 approached Uranus in January of the year 1986. At closest approach, it passed within about 81,500 kilometers of the planet's cloud tops. What it saw was unexpected. Uranus's atmosphere appeared calm and almost featureless, lacking the dramatic bands and storms seen on Jupiter and Saturn. It challenged assumptions about how gas giants behave. In false color images, subtle differences emerged. Especially near the poles, regions tilted dramatically because Uranus spins on its side, with an axial tilt of about 98 degrees. But an even greater shock came from Uranus's magnetic field. Before Voyager, no one knew for certain whether Uranus had one at all. Voyager revealed not only that it does, but that it is wildly misaligned. Uranus's magnetic axis is tilted by about 59 degrees relative to its rotation axis. On Earth, the difference is only about 12 degrees. This meant that Uranus's magnetosphere, the bubble carved out by its magnetic field, wobbles dramatically as the planet spins. Like a poorly thrown football tumbling through space, it defied existing models and forced scientists to rethink how planetary magnetic fields can form. Voyager 2 also refined our understanding of Uranus's rings, confirming known ones and discovering 2 more. These rings are dark, narrow, and composed of fine dust. As with Saturn, Voyager found shepherd moons guiding one of the rings, reinforcing the idea that small moons play a crucial role in shaping ring systems. The spacecraft captured images of these moons from about 4 million kilometers away in January of the year 1986. Before Voyager, only 5 moons were known to orbit Uranus. Voyager imaged those 5 for the first time and discovered 11 more, bringing the total to 16 at the time. Today, we know of 27 Uranian moons. Voyager's data provided the first measurements of their sizes, compositions, and orbits, transforming them from names on a list into real worlds. The 5 largest moons, Oberon, Umbriel, Ariel, Titania, and Miranda, appeared to be mixtures of ice and rock, similar to Saturn's moons, Oberon and Umbriel, seen clearly in January of the year 1986, were heavily cratered and dark, suggesting ancient, inactive surfaces. Titania, larger and closer in, told a different story. Vast fault systems and deep canyons scar its surface, hinting at tectonic activity in its past, a sign that even here, in the cold and distant reaches of the solar system, worlds have histories written in motion and change. Ariel, in contrast, looked almost bright enough to feel new. Among Uranus's larger moons, it has the lightest surface, and Voyager's close view hinted that it may also be the youngest looking. From a distance of about 129,000 kilometers, the photograph showed long fault valleys and broad flows of icy material, signs that, at some point in its past, Ariel did not simply sit frozen and unchanged. Something inside it once shifted, cracked, and resurfaced the shell, leaving behind scars that still catch the light. And then there was Miranda Small, close to Uranus, and quietly shocking. It orbits nearer than the other 4 large moons, second only to a smaller satellite called Puck, discovered shortly before Voyager's arrival. Miranda was the moon that seemed, at first, too modest to hold much drama. But when Voyager 2 swept past on the 4th of January in the year 1986, passing only about 30,000 kilometers away, that assumption fell away almost immediately. Miranda's surface looked like a world assembled from mismatched pieces. The images suggested traces of internal melting long ago, and sporadic upwellings of icy material that may have pushed upward from below. Deep, canyon-like faults cut across the landscape, plunging down to depths of up to about 20 kilometers, gashes so large they feel out of scale for such a small body. Elsewhere, oval features appeared, shaped like racetracks scratched into the moon, as if the surface had been pulled and dragged in slow motion. Voyager also revealed terraced regions and sharp boundaries where old terrain and young terrain sat side by side, bright beside dark, heavily cratered beside smoother plains. One pattern, a chevron-like texture, looked as though Miranda's original crust had been torn apart and then forced back together. Fragments reassembled into a patchwork. It was difficult to look at and not feel the echo of a volatile past, an object that should have been quiet, but wasn't. About 3 weeks later, on the 25th of January, Voyager 2 departed Uranus and took a final farewell image from roughly 1 million kilometers away. Uranus shrank into a pale, distant disk, and the probe set its course for the last planetary target of its grand tour. For 3 years it traveled onward, moving at about 54,000 kilometers per hour, until Neptune finally rose into view. On the 25th of August in the year 1989, more than 12 years after leaving Earth, Voyager 2 approached the farthest major planet in our solar system and delivered the first close-up images humanity had ever seen of that deep blue giant. The flyby was breathtakingly close, only about 5,000 kilometers above Neptune's North Pole. Closer than any other spacecraft would ever come. Voyager found hydrogen to be the most common element in Neptune's atmosphere, with methane playing a special role in what we see. Methane absorbs red light, leaving more blue to scatter back towards space. And that is part of why Neptune wears its intense color like a cloak. But the real surprise was not the hue, it was the violence of the winds. Voyager measured extraordinary speeds, with equatorial winds reaching nearly 1,100 kilometers per hour, weather far more ferocious than many expected so far from the sun. Neptune's storms were not subtle either. Scientists found a massive rotating feature that became known as the Great Dark Spot, a tempest that felt like a distant cousin of Jupiter's Great Red Spot. It seemed to rotate counterclockwise, and in places, winds within it were estimated to reach up to about 2,400 kilometers per hour, the strongest recorded in the solar system at the time. People working with the data described the feeling of watching a world no one had ever truly seen before, day by day. The details were new, and changes appeared to happen quickly, as if Neptune's atmosphere had been waiting to show its true nature only when an eye finally arrived. Voyager 2 also imaged Neptune's rings for the first time. For years, scientists had suspected rings might exist, but certainty was elusive until Voyager's cameras and instruments confirmed them. Even then, Neptune refused to be simple. The spacecraft identified partial ring structures, arcs, incomplete segments of dusty ring material that did not form a smooth, continuous band. Their existence raised a gentle but persistent question: how do such arcs remain stable over time? Instead of spreading into full rings or dispersing entirely, a Neptune encounter would have felt unfinished without visiting Triton. The planet's largest moon, Triton, turned out to be astonishingly cold. Among the coldest planetary bodies we know, it showed a fractured surface and active geyser-like eruptions that lofted material above the ground. Near its southern pole lay a pinkish nitrogen ice cap, softly tinted and strangely beautiful. Dark plumes were also seen, streaks that hinted at cryovolcanism. Ice volcanoes, driven not by molten rock, but by volatile ices and gases. Voyager 2 discovered 6 new moons around Neptune as well, adding more quiet companions to that distant system. When the flyby was complete, Voyager 2 turned to take one last look at Neptune and Triton. With that final glance, its grand tour was finished. Neptune's gravity bent its trajectory downward, out of the ecliptic plane, the broad, flat plane in which most planets orbit. From there, Voyager 2 continued outward into interstellar space, following the same long destination Voyager 1 had been set on 9 years earlier. Voyager 1, meanwhile, had been traveling steadily since it last left Saturn behind, about 1 year after Voyager 2's Neptune encounter. Voyager 1 was already roughly 6 billion kilometers from Earth. To conserve power for the long journey ahead, the team planned to shut its cameras off forever. But at the urging of Carl Sagan, they made one last decision that was not about planets, but about perspective. They turned the camera back toward home. On the 14th of February in the year 1990, Voyager 1 took what is often called the most remote selfie ever captured, a distant portrait of our world from about 6 billion kilometers away. Earth appeared as a tiny point caught in a beam of sunlight, the pale blue dot. Sagan's reflection on that image was not a technical analysis so much as a quiet moral weight that everything we care about, every life ever lived, every joy and sorrow, happened on that small speck. The picture is humble, and the humility lingers, even now. Decades later, it still nudges the mind toward tenderness, toward the idea that we should be kinder to one another, and careful with the only home we have ever known. And yet, the voyage did not end with a photograph. Leaving the ecliptic was only the beginning of the truly strange part of the journey. Voyager 1 escaped the plane of the planets, heading about 35 degrees to the north, while Voyager 2 later went about 48 degrees to the south to reach interstellar space. Both had to cross invisible boundaries, regions shaped by the sun's influence and its collision with the wider galaxy. First came the termination shock, where the solar wind, charged particles streaming outward from the sun, runs into strong resistance from the interstellar wind. Beyond that lies the heliosheath, a region where the slowing solar wind piles up, becoming denser and hotter. Farther out still is the heliopause, the final boundary where the sun's outward flow is effectively stopped, and the interstellar medium begins to dominate. Even so, crossing into interstellar space does not truly mean leaving the solar system in every sense. The solar system's distant reservoir of icy bodies, the Oort cloud, is staggeringly far. It may take about 300 years for Voyager 1 to reach it, and about 30,000 years to pass through it completely, timescales so long they feel like geology, not travel. As the probes moved through the heliosheath, they discovered that the boundary regions were messier than expected. The sun's magnetic field is wound up by the sun's rotation, and because the field points in opposite directions in the north and south, the structure forms a rippling sheet where those regions meet, called the heliospheric current sheet, like wave rings spreading outward after a stone is dropped into water. Voyager's data suggested that when those magnetic ripples reach the termination shock, they compress, stacking up as if the waves had reached the edge of a pool. Beyond the shock, those piled ripples appear to form magnetic bubbles, implying the heliosheath is not a smooth, clean shell, but a fluctuating environment full of tangled magnetic structure. That single finding forced scientists to revise how they model the heliosheath itself. On the 25th of July, in the year 2012, Voyager 1 became the first human-made object to leave the sun's heliosphere and enter interstellar space. It was traveling at about 540 million kilometers per year, roughly 3.6 astronomical units per year. With 1 astronomical unit meaning the average distance between Earth and the Sun, The crossing occurred at about 120 astronomical units from the Sun, an important surprise on its own. Because the heliopause distance had been uncertain, early models placed it wildly differently, some imagining it far closer, others far beyond. The heliopause can be pictured as the meeting place of two flows, the solar wind pushing outward, and the interstellar medium pressing inward. The solar wind is a steady stream of charged particles, electrons, protons, and alpha particles blown from the Sun's outer layers. The interstellar medium, by contrast, is a thin mixture of charged particles, gas, and cosmic dust, shaped by ancient events like supernovae and the long evolution of the galaxy. Where these streams collide, they bend and change, forming a boundary region that is less like a wall and more like a shifting shoreline. At first, NASA was cautious about declaring victory. Voyager 1's plasma wave instrument detected a large increase in plasma density on the order of 80 times what it had registered in the outer heliosheath, and galactic cosmic rays spiked, both consistent with entering a new environment. But one expected change did not appear. Voyager 1 detected no clear shift in the ambient magnetic field direction. Models had assumed that in a region dominated by interstellar magnetic fields, the orientation would noticeably change. The lack of that change was baffling enough that NASA waited nearly a year before officially announcing that Voyager 1 had, in fact, entered interstellar space. On the 5th of November in the year 2018, Voyager 2 joined it, becoming the second human-made object to cross into interstellar space. Voyager 2 was traveling a little more slowly, about 490 million kilometers per year, roughly 3.3 astronomical units per year. Its heliopause crossing also occurred at about 120 astronomical units from the Sun. And just like Voyager 1, it detected no obvious change in the ambient magnetic field direction. Voyager 2's crossing delivered another quiet surprise. The Sun runs through an 11-year cycle of activity, waxing and waning. Voyager 2 crossed at a time when solar winds were near a peak. Models suggested the heliosphere should breathe with the cycle, expanding outward during stronger solar wind periods. If that were true, Voyager 2 might have crossed farther out than Voyager 1 did. Instead, it crossed at essentially the same distance, hinting that our models were missing something important. Along with the magnetic field puzzle, it suggested the boundary between the heliosphere and the interstellar medium is more twisted, more fluctuating, and more complex than earlier theories proposed. One leading idea is that long ago, billions of years in the past, our Sun emerged from a hotter, more heavily ionized region shaped by one or more nearby supernova explosions, and that magnetic turbulence from that history still lingers near the heliopause. If so, the probes may encounter a different magnetic orientation as they travel farther away, though by then, their instruments will likely be long dark, even if their radios still whisper to us from the dark. The Voyagers are old ships now, and age shows itself in quiet, strange ways. In early May of the year 2022, Voyager 1 began to sound wrong. Imagine you are one of the engineers who has spent years listening to this spacecraft's steady heartbeat. You sit down at your computer and open the latest telemetry, those routine status updates that tell you what Voyager believes about itself, how it's oriented, what its thrusters are doing, which systems are healthy, which ones are tired. But conversation with Voyager 1 is slow now. The probe is so far away that a signal takes about 22 hours to reach Earth. When you send a command, you wait like someone sending a letter across an ocean and hoping the reply will come back someday. It's not a quick back and forth. It's patience, stretched into a workday. And today, the letter arrives filled with nonsense. Instead of clean, meaningful numbers, you see long strings of zeros, or a repeated value that keeps showing up 377 over and over, as if the spacecraft has forgotten how to speak in its usual language. The data claims things that cannot be true, that Voyager is pointing in directions it couldn't possibly be pointing. It suggests motion that cannot be happening. So you do the first simple check. Did you really receive a signal from Voyager 1? Yes. There it is. Present and clear. And not just present, its strength is normal. 2. That matters. Because Voyager's antenna is narrow-beamed. If it truly were pointing off into space the way the bad telemetry claims, the signal would fade or vanish. But it hasn't. The probe must still be aimed at Earth. Steady and faithful. Just as it has been for decades. Then something even stranger happens. The science data arrives. And it looks fine. Over the years, Voyager 1 has had to power down equipment to conserve energy. Out of its original 11 instruments, 5 have been turned off intentionally, and 2 more have stopped functioning through natural degradation. But the remaining 4 are still doing their quiet work, taking readings of the interstellar medium, magnetic fields, and cosmic rays. And those readings are not garbled. They are coherent. They look like Voyager 1 is still truly out there, still sensing the invisible texture of space beyond the sun. You check the power situation. It is low, but not surprising. Voyager's generators rely on plutonium oxide, and the isotope's half-life is about 87 years. Voyager 1 has been traveling for about 45 years now. Decline is expected. People have long believed the spacecraft might not last beyond the year 2025, but that's still some distance away in time. And it doesn't explain why the probe suddenly began sending nonsense today. So you narrow it down. You look through subsystem after subsystem. Most of it looks stable. Only one system is behaving strangely, the AACS, the Attitude and Articulation Control System. That name sounds technical, but its job is intimate. It is the part of Voyager 1 that helps keep the spacecraft properly oriented, so its high-gain antenna stays pointed at Earth, so it can keep hearing us and answering back. And now, this system has stopped sending coherent data. It's an unsettling kind of problem, because it resembles a familiar routine that has subtly broken, like a mail carrier who still arrives at the right address, still delivers the right packages, still smiles the same way, but suddenly speaks in sounds you cannot understand. The delivery is intact. The language is not. To make it more puzzling, Voyager 1 does not seem worried. The spacecraft has safe mode behaviors designed for emergencies, procedures that power down and wait if something critical is wrong. But none of those have activated. Voyager 1 is behaving as if everything is normal. It believes itself healthy, even while it's speaking nonsense in one of its most important voices. This is the scene NASA faced in the middle of the year 2022. A single fault like this might seem small, just a computer glitch, just a garbled stream, but in deep space, It hints at deeper trouble. If one system is confused, could others follow? Could this be the start of a slow unraveling? And Voyager 1 is far beyond any helping hand. It is about 23.8 billion kilometers away. Every question you ask takes 22 hours to arrive. Every answer takes 22 hours to return. You have to solve the puzzle by deduction, like a doctor diagnosing a patient by letters alone. There are some explanations you can gently set aside. The science data looks normal, so the laws of physics probably haven't broken. There's no reason to believe the spacecraft has slipped into some impossible shortcut through space while still keeping its radio aimed neatly at Earth. And no, this is almost certainly not aliens trying to talk by scrambling telemetry. It's true the Voyagers carry golden records, messages meant for any distant intelligence that might someday find them, but those were symbolic invitations, not an expectation of contact. And if something out there wanted to communicate, this would be an odd way to do it. The simplest, kindest answer is usually the right one. The problem is likely inside the AACS itself. For months, engineers tested ideas carefully. Because every command carries risk. Voyager 1 is built with redundancies. It has backup pathways, alternate hardware, the ability to switch between units if one fails. It wouldn't even be the first time such a switch had happened. A previous AACS computer had become defective earlier in the mission, and Voyager had moved on to another. The team considered moving to a backup again. They also considered leaving the issue alone, because the science data was still arriving. Could Voyager simply carry on, speaking gibberish in its housekeeping language while still doing the important work? But the garbled language implied something more than inconvenience. It suggested the possibility of a deeper confusion, an error that might spread, or an unnoticed shift that could eventually affect pointing, communication, and survival itself. So they kept probing, slowly and carefully, like tapping on a wall to find where the hollow spot is. The truth turned out to be almost simple, in a way that feels both relieving and unsettling. In the radiation-filled environment of deep space, something had caused Voyager 1 to start routing its telemetry through the older, already broken AACS computer, the one that should not have been trusted anymore. That faulty unit corrupted the data, producing the strange strings of zeros and the repeated numbers. So the fix, conceptually, was straightforward. Tell Voyager 1 to use the correct computer again. But even straightforward is slow when your conversation moves at 22 hours per message. It still took months for Voyager 1 to return fully to normal behavior, for the wrong routing to be undone and the old ship to steady its voice again. And that wasn't the end of the aging signs. In November of the year 2023, another onboard system, the flight data subsystem, developed a similar issue, becoming unable to send usable science and engineering data. That problem was not fully resolved until June of the year 2024. Voyager 1 keeps moving, but it also keeps reminding us that time is not gentle to machines, even heroic ones. Voyager 2 had its own close call. In July of the year 2023, a routine command sequence caused the probe to angle its antenna away from Earth by 2 degrees. 2 degrees sounds tiny, almost nothing. But over interstellar distances, that slight misalignment was enough to break the link. NASA could no longer hear Voyager 2, and Voyager 2 could no longer hear NASA. For a while, it was simply gone, still out there, still moving, but silent. The recovery required a kind of long-distance shout. Engineers used the Deep Space Network facility in Canberra, Australia, to transmit a powerful command telling Voyager 2 to reorient itself back toward Earth. Then came the waiting, about 37 hours, for the command to arrive and for any reply to return. It must have felt like holding your breath without ever meaning to. The probe could have been lost forever. But it answered. It turned back. The thread was restored, one way or another. The end is inevitable, whether through malfunction, error, or simply running out of power. There will come a day when the Voyagers stop speaking to us. The curtain will fall on this incredible mission. And yet, even then, their journeys will only be beginning in the larger sense. They will keep drifting, quiet and intact, across the Milky Way. In about 40,000 years, Voyager 1 is expected to pass near a star in the constellation Camelopardalis. Voyager 2, on a slightly different path, will pass about 1.7 light-years from the star Ross, 248, and in about 296,000 years, Voyager 2 is expected to pass about 4.3 light-years from Sirius. These timescales are so long, they make human history feel like a breath. The probes may outlast the Earth itself, continuing their solitary wandering long after the names Voyager and NASA have become dust. And if chance ever brings them near intelligent life, they carry a small introduction, a message to the stars. Each spacecraft holds a golden record, a set of audio and visual materials meant to offer distant strangers a glimpse of Earth. Photographs of our world and its life, the sounds of whales and babies crying, music by Mozart and Chuck Berry, greetings spoken in 55 languages, a little bundle of who we were, placed gently on a machine we sent away forever. For us, there is nothing to do but say goodbye, again and again, in slow stages, as their signals dim, and to hope that this was not our last brush with the stars, but only the beginning. And that hope leads naturally into a quieter, deeper question, one that feels almost like it belongs to the universe itself. Is space truly inescapable? If we could somehow overcome the limits of the speed of light and travel toward the farthest edge, what would we find? More space, stretching without end, endless planets and systems, or something stranger, some path that loops back, bringing us to where we started amazingly. Scientists have considered all of these possibilities, and which one is true depends on the shape of the universe, on the nature of that unseen structure surrounding everything we've been talking about. So, before anything else, it helps to begin with a concept you already know. Even if you've never held it gently in your mind for very long. Infinity. In mathematics, infinity is the idea of something so large it can't be beaten. Of course, no single number is truly infinite, because for any number you name, there is always another number that is at least one larger. In that sense, the point of infinity is not a final value, but the fact that there is always more, always another number waiting beyond the one you thought was last. And when we turn that idea of infinity toward the real universe, we run into a quiet fact so far. We have found no edge, no wall, no final boundary where space simply stops and says, "This is enough." Every time our telescopes grow more powerful, the darkness steps back a little, and what it reveals is not emptiness, but more light. Even the blackest looking patches of sky can bloom into crowded fields of distant stars and galaxies once you let an instrument stare long enough. That kind of endlessness can feel almost unsettling, because our daily lives are built from endings. Rooms have walls. Roads have borders. Stories close their covers. So the thought that there might be endlessly more worlds, more planets, more suns, more places where physics is quietly doing its work can be hard to hold in the mind without it slipping away. But infinite does not automatically mean everything imaginable exists in endless quantity. There are different ways a universe can be infinite, and different ways it can feel infinite while still containing only a finite amount of stuff. The shape of space matters, and when scientists talk about the universe's overall geometry, there are three broad possibilities that often come up: a flat universe, a spherical universe, or a hyperbolic universe. A flat universe is the simplest to picture. If you drew a giant grid across reality, the lines would behave the way we expect. Parallel lines stay parallel, and perpendicular lines meet at right angles. If space is flat in this global sense, then it can extend forever, in every direction, an endless plane of distance. It's also, in a way, how the universe feels locally. When you look outward, most directions look straight. The sky doesn't obviously curve. For everyday purposes, space behaves like a calm, open expanse. But gravity reminds us that straight is not always as simple as it sounds. Think of the strange images we can make of a black hole. Bright rings seem to appear above and below it, as if the glow wraps over the top and under the bottom. In reality, those extra rings can be an illusion created by bent light. Light from the far side is pulled around by intense gravity, curving into our line of sight. So we can end up seeing parts of the same ring from multiple angles at once. It's not that the black hole wears extra bands like jewelry. It's that gravity changes the paths light can take. That bending leads naturally to the second possibility: a spherical universe. In a spherical geometry, the rules of lines change. Instead of staying neatly parallel, lines that begin parallel eventually converge. Try drawing two parallel lines on a sphere. You can start them off side by side, but if you keep going far enough, they will meet like lines of longitude on Earth that touch at the poles. In a universe with this kind of overall shape, traveling straight for long enough might bring you back to where you started. Space would feel endless because you could keep going without hitting a boundary. But the total volume could still be finite, more like walking around a planet than walking on an infinite plane. In that kind of universe, the idea gets playful in a slightly eerie way. If light could travel fast enough and circle the cosmos, you could, in principle, receive light that left you long ago, almost like looking at your own history from behind. It's a strange thought, and it hints at how geometry can turn infinite travel into finite space. We do have evidence that space can behave in a curved way, at least in regions near massive objects. Gravity doesn't just pull things in the everyday sense. In the language of modern physics, mass and energy shape space-time itself, changing what straight means. A black hole is the most dramatic example. Inside its event horizon, the geometry becomes so warped that every path you could take still leads deeper inward. No direction points outward in a way that allows escape. It's like being inside a kind of one-way landscape. And then there is the third possibility, the one that feels hardest to picture but carries a simple rule: hyperbolic space. Here, instead of lines staying parallel or bending toward each other, they diverge. Everything spreads away from everything else. If you try to draw a tidy grid in hyperbolic geometry, the squares begin to look distorted, not because they stop being squares within that geometry, but because the space itself is expanding away as you try to lay the pattern down. You can even get strange outcomes, like more shapes meeting at a point than would ever be possible in ordinary flat space, because there is simply more room than your intuition expects. To make sense of this without getting lost, it helps to lean on a gentle picture: the relationship between space and time. Imagine timelines as paths pointing forward into the future. In your own experience, time moves forward steadily. Space is what you move through sideways, closer to something, farther away. Left or right, in the broad sense. When a large mass appears, it warps those timelines. A path that would have gone straight forward begins to tilt toward the mass. That tilt is what we experience as gravity. You are not being pulled by an invisible rope so much as following the new shape of what counts as a straight path in a warped landscape. Now bring that idea back to hyperbolic space. In a hyperbolic universe, the overall geometry encourages separation. Parallel lines don't stay the same distance apart. They drift farther and farther apart. And that should sound familiar, because on the largest scales, that is what we observe. Galaxies, on average, recede from one another as the universe expands. Inside a galaxy, gravity holds things together, so you don't notice this expansion in your daily sky. But between galaxies, over truly vast distances, the trend is outward. Scientists often describe the driver of that accelerated expansion as dark energy. But another way to wonder about it is to ask whether the universe's shape itself might naturally behave in a hyperbolic way. If space were truly hyperbolic on the largest scale, it would not only be infinite, it would be more than infinite in a certain geometric sense, because the amount of space you gain as you move outward grows faster than it would in a flat geometry, like opening a door and finding not one corridor, but branching corridors, each leading to more branching corridors. It is an image, not a proof, but it helps the mind feel why hyperbolic space can seem so explosively roomy. There is a cost to that kind of shape. 2. If everything keeps drifting apart, then over enough time, distant galaxies could fade beyond our reach until only our local region remains visible. The wider universe would still exist, but it would be hidden behind distance and expansion, like a shoreline disappearing into fog. So what do observations say when scientists measure the universe's large-scale geometry? It appears very close to flat, at least within the limits of what we can currently detect. That doesn't completely erase the other possibilities, but it does suggest that if the universe is curved, the curvature is subtle, and subtlety is the universe's favorite way of being difficult. It leaves room for a softer, blended thought. Maybe space has a tendency to spread, and matter has a tendency to pull together, and the two effects can offset each other in a way that makes the cosmos look nearly flat from where we stand. Perhaps different regions behave differently. Perhaps what feels like one clean model in our equations is, in reality, a delicate balance of influences. We don't have the final answer yet, but the question itself is worth keeping not as something to solve in a hurry, but as something to let sit gently in the mind, the unseen structure of space, the shape beneath everything we see, may be more influential than we currently realize. Long before telescopes and satellites, people sat close together around a single fire and stared into the surrounding dark, wondering what might be out there, what might be moving, unseen, just beyond the reach of their light. In a quiet way, we still do the same thing. Our campfire is simply larger now. It glows through mirrors and sensors, through instruments like the James Webb Space Telescope, reaching not just across oceans and continents, but outward to the farthest limits of what we can observe. And still, there is always an edge. Not an edge you could sail to, or walk up to and touch, but a boundary set by physics itself. The observable universe has a horizon, an impenetrable line where space is expanding away from us so quickly that anything beyond it can never send a signal that reaches us. Not light, not information, not cause and effect. Beyond that horizon, whatever exists is cut off from us in the deepest sense. We can't reach it, and it can't reach us. The darkness there isn't just unseen, it's unreachable. Or at least, that's how it seems at first. Because in the year 2008, something unsettling was reported when researchers analyzed the motion of many galaxy clusters. They found hints that clusters were drifting in a shared direction, faster than expected, almost as if something far beyond our visible boundary had once tugged on them. A pull stretching across billions of light years, a suggestion that the universe might have a kind of current, carrying matter along. This proposed motion was given a name that sounds like a whispered dark flow. The idea is controversial, so it helps to begin with the solid ground beneath it. In the year 2001, NASA launched a spacecraft called the Wilkinson Microwave Anisotropy Probe, often shortened to WMAP. Its mission was to map the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space. This background is like a cooling ember from the universe's earliest time. And by mapping its tiny temperature variations, scientists learned profound things about the universe's geometry and the relative roles of ordinary matter, dark matter, and dark energy. The map was completed in the year 2010, though important data releases came earlier and quickly became central to cosmology. One scientist especially eager to use that data was Alexander Kashlinsky. Leading a team at NASA's Goddard Space Flight Center, they wanted to compare the cosmic microwave background map with the motion of galaxy clusters, searching for patterns. To do this, they leaned on an extremely subtle technique called the kinematic Sunyaev-Zeldovich effect, a tiny imprint left when cosmic microwave background photons pass through hot, energetic galaxy clusters. In simple terms, as that ancient light travels through a cluster, it can gain a slight energy nudge if the cluster is very hot, or if it's moving in a particular way. That nudge changes in a measurable pattern, barely measurable, but not impossible. The catch is how small the signal is. You can't rely on a single cluster. You need many. And you need statistics. And you need a background map detailed enough to compare against. Kashlinsky's team gathered around 1,000 known galaxy clusters and searched for a shared motion relative to the cosmic microwave background. And they reported a surprise, a broad bulk flow extending roughly 2.5 billion light-years, with clusters moving at hundreds of kilometers per second, around 600 to 1,000 kilometers per second, toward a region of the sky near the constellations Centaurus and Hydra. The puzzle was not that clusters move. They do. The puzzle was that this motion seemed too coherent across such an enormous scale, with no visible structure within our observable universe large enough to account for it. If gravity were responsible, the tug would have to come from something massive and possibly from beyond the edge of what we can see, which raises a delicate question. Can anything beyond our cosmic horizon influence us at all? If beyond the horizon means no signals can reach us, it's tempting to say, no light, no gravity, no interaction of any kind. But cosmology contains a subtle loophole. What matters is not only where things are now, but whether they were ever in causal contact in the early universe. This is where cosmic inflation enters the story. Physicists in the 1970s faced a mystery called the horizon problem. Distant regions of the universe look remarkably similar in temperature and structure, even though, under simple expansion, they shouldn't have had time to talk to each other and even out. Alan Guth proposed that a brief episode of extremely rapid expansion occurred very early on after the Big Bang, began stretching a once-connected region into the vast cosmos we see. The details can get heavy, but the takeaway is, gentle inflation allows parts of the universe that are now unreachable from one another to have once been close enough to interact. So, in the dark flow interpretation, one possible story goes like this. Before inflation fully stretched everything apart, our region of the universe may have been slightly tugged by a denser area elsewhere. Inflation then expanded space so dramatically that the source of that tug is now far beyond our horizon. The pull would no longer be acting on us today, but the motion it started could persist because things in motion tend to stay in motion unless acted upon. Galaxy clusters would then still drift in that same direction, like leaves carried by a current long after the wind that started it has passed. It's a story with a certain eerie elegance, but it is controversial for two main reasons. The first is what it implies about the universe beyond our horizon. Dark flow would require an extraordinary concentration of mass outside our visible region, enough to have once influenced enormous structures. That clashes with a core expectation in cosmology that on large scales the universe is roughly homogeneous and isotropic, meaning matter is evenly distributed and no direction is special when you average over enough space. Dark flow would suggest that just beyond our observable edge, the universe might stop being so uniform. That's not impossible, but it is a profound shift, and it raises uncomfortable questions about whether we live in an unusually smooth patch by cosmic luck. The second reason is simpler. Dark flow might not exist at all. After WMAP, another spacecraft, ESA's Planck mission, launched in the year 2009, produced an even more detailed map of the cosmic microwave background. The Planck team examined galaxy clusters too, and reported that they saw no clear sign of the dark flow pattern. Kashlinsky's team, looking at Planck's data, argued that the signal is still there. So the debate remains. Proposed follow-up analyses combining Planck and WMAP have been discussed, but without a decisive, widely accepted result. The cautious position is to assume the phenomenon is unconfirmed. So for now, it's reasonable to imagine there is no hidden boogeyman beyond the horizon, no unseen giant mass dragging the cosmos in one direction. And yet, The question lingers in the same way the night used to linger beyond the campfire's glow. Science doesn't choose what's comforting. It follows what's true. Whether the answer is simple or strange, maybe one day we will know more clearly what lies beyond our visible universe, whether the boundary is only an observational limit or a deeper division in reality. And if we do learn more, the pattern will likely repeat. The darkness will retreat. Just a little, and a new edge will appear. There is always more to wonder about. And we keep returning to that quiet human habit, standing at the border of what we can see, letting curiosity lean gently into the unknown.